Okay, so this talk, the inspiration for this talk is I was playing disc golf with one of my friends who works at a physics department, programs in Fortran. And we were talking, and so he tells me, oh, you know, sometimes I use goto statements. And I was thinking, wow, I thought those didn't exist anymore. And so I was like, buddy, you really got to use while loops. Like, don't use goto statements. But then I was thinking, well, actually, no, like, don't use while loops. You want to use recursion. And then, but then I was like, well, I work at Slam Data, and in a lot of our code base, we developed this library called Matryoshka, which is Recursion Schemes. And we try and avoid recursions. We even have this wart enabled on our code base, which forces us to put a warning whenever we use explicit recursion. And so I was actually, don't really use recursion. But I figured maybe I should just tell him to use while loops to start. And so just wanted to go through, so yeah, this was the inspiration for the talk. So it started off, we had unstructured programming. And I think this is kind of funny because it reminds me of imperative programming. When people invent a new paradigm, they're usually pretty arrogant about how they call the previous paradigm. For instance, you know, probably a lot of people here are, you know, you guys agree functional programming is pretty good. But when we call mainstream programming imperative, it has this idea that we're like completely declarative, as if like when you're writing Haskell and Scala, you're not telling the computer at all what to do. You're just describing the problem. And let's be honest, I mean, we're programming at a higher level, but we're still pretty much telling the computer what to do. So I think this is pretty funny that you know, we say, oh, that's completely unstructured programming. I don't know. It's pretty arrogant. It seems pretty arrogant to me. But basically what it is kind of unrestricted use of gotos, which, you know, has the benefit of being close to the machine. But after a certain amount of time, we realized that this kind of leads to spaghetti code. And we realized that there was some common patterns that emerged from languages that kind of force you to use goto statements. And so basically, there were patterns that were accepted. OK, you can use goto statements in this way, and other patterns that were not accepted. And so what we did is we invented structured programming. And structured programming is very sophisticated, has loops and subroutines, which we would probably call functions. Switch statements or conditionals, if, else. In Scala, we have match, which is pretty nice, and exception handling. So like these, you probably recognize as what you'd use when you're coding in Java, C#, something like that. Vastly superior to goto statements, I would say. Anyway, so we refer to this as structured programming. But the thing is, if you have subroutines, then why not use, oh, I forgot I had one more bullet point there. So this is taken from the paper lens, bananas, lens, barbed wires, and something else. I'm forgetting all the names of the rooms. And they mentioned that structured programming, reasoning about programs becomes feasible and sometimes even elegant with structured programming. I thought that was pretty funny. But yeah, so if we have subroutines, then why not use recursion? I think recursion is elegant, succinct, and ironically, with tail call optimization, we actually kind of rewrite it to look a whole lot more like a while loop in the machine level. Has anyone ever seen someone during a coding exam or something try and code a problem that has a really elegant recursive solution using loops? It's usually pretty cringeworthy. So I wanted to, so then here comes this paper, Functional Programming with Bananas, Lenses, Envelopes, and Barbed Wires. And it introduces banana notation, in case you guys were wondering where that comes from. It also introduces lenses notation. It introduces envelope notation. And finally, it introduces barbed wire notation. So the idea behind recursion schemes is to extract the common recursive patterns that we use when we do recursion. So you'll notice very similar to what we're doing when we're going from goto statements to while loops. Basically, it enables higher order recursion and is probably even more succinct than recursion already is. So here's another quote to kind of repeat what I said. This philosophy is similar in spirit to the structured programming methodology for imperative programming. See, the arrogance is coming through again. So what are some of the common patterns? We don't need to go and look at Matryoshka, which some of you guys might think is scary. We just have to look at the standard library. So functions such as length, filter, fold are all, length is, well, yeah, they're all recursive algorithms or patterns. And basically they show up so often that we've extracted them and we reuse them. In this case, length and filter can be expressed as fold. Fold is probably one of the fundamental, most recursive algorithms on lists can probably be expressed with fold. There's also unfold, which is interesting. Unfold is not in the Scala standard library, but I think it should be. So the idea is you give it a seed value and you can produce a list by applying successively a function that returns some if there's should be another element in the list, and then new seed, and then none if this should be the end. And here's just an example where we compute the prefixes of a directory by calling the parent directory to which gives us the parent directory as an option, and we strengthen we add the directory to that. So basically, this is just like a very short implementation of prefixes for a directory using unfold. So this stuff you're probably pretty familiar with. So this, I just wanted to show it because this really is the essence of recursion schemes, right? It's the idea of that we want to use recursion. Recursion is a good thing to use, but we can sometimes extract patterns and reuse those. So what are the patterns that we find in recursive algorithms? So there's the catamorphism. Can anyone tell me what cata means? Destruct? Close. It means downwards. So it's this idea that we're delving downwards into the structure of our recursive data type. What about anamorphism, or ana?
Again?
No, not quite. Although some of these words have multiple meanings, the one that I chose was upwards. So the idea of ana is basically, so cata is basically very similar to the fold that you see on the Scala standard library list. Ana would be the unfold. So ana starts with a seed value, and then you build up a recursive structure by continuously kind of destructuring that seed value. What about high-low? This one's pretty tough. No? No one? So high-low means dust or matter. And in the paper, they actually mention that that they chose it because it means dust or matter, but I don't know why they chose dust or matter. And then paromorphism. So paromorphism is basically a catamorphism, except that during the recursive algorithm, you get to see both the computed value and the previous value. And so what para means is alongside. So you get a tuple, basically the old value alongside the new value. So in the paper, this is the notation they use. So we've got our banana notation up there. And so they're defining two functions. The first one is length. And the idea here is we're saying that, okay, let me show you here the Scala code that's equivalent to basically the notation in the paper. Because it took me a little while at first when I was looking at this notation, I was like, whoa, what does this mean? And what it really means is that basically the argument on the left is what should be essentially returned when you see the leaf element of the list, of the list. And then the second element is the combination function. So here, length, we're saying, well, if we see the end of the list, it's 0, and then our combination function is going to be 1 plus n. And so in Scala, this is what it looks like. Nil maps to 0, and then cons would be adding 1 to our n. In the case of filter, if we look at the notation at the top, we're starting off nil. So if we encounter a nil, then filtering should still be nil. And in our combination function, this is a mathematical notation. We're saying that if we encounter a cons, that we apply our predicate P to A, and if it's true, then we return the cons, and if it's not, then we just return the tail of the cons. And if we look at the Scala code at the bottom, we see that that's kind of the equivalent in coding. So nil maps to nil, and then cons, we look at whether P returns true. If so, we add the X back into the list, return that. If not, return the tail. Let's look at anamorphism now. So an anamorphism, for instance, in this case, a zip, where in the paper they're using the lens notation to represent the operation. So the idea here is we get a tuple with two lists, and we want to return a list of tuples. And so they represent, this one's interesting because I actually don't fully understand. So it takes two arguments. The first one is a predicate basically saying whether we're finished unfolding. And then the second one is the function that actually performs the operation. But it seems to me that we don't actually need the predicate. So in the equivalent Scala notation here, we're saying that if both are empty, well, actually, yeah, I just realized that at the top in the predicate they're looking at if either of them are nil, we stop. And whereas here, this pattern match is not exhaustive, but get an exception. But anyway, assuming that both lists are of the same length, then you would produce an empty list, or else you kind of rehash things together to do one step of your operation. Yes?
I'm new to this. First time I heard the term anamorphism. Can you give me an intuition why this code is going upwards?
Yeah. So the idea here, I understand what you're saying because this function zip is kind of taking lists to lists, so it doesn't feel like it. But the thing is, so when we're thinking of upwards, is we're thinking of taking a value that's like a discrete value, like a single thing, and producing a recursive structure. But what can be confusing sometimes, and this can happen as well when you're doing a kata, is that sometimes the return value, so a kata would be the contrary, right? You take a recursive structure such as a list or a tree, and you produce it down to a single value. So when we're computing the length or computing like some kind of cost associated with a tree, the result might be an int, and then it's very easy to understand that you're going from a complicated tree to an int. But the problem is a lot of kata algorithms actually produce like a somewhat recursive structure, right? So they'll produce a new list. And then, so if you go from list to list, like in the left-hand side, it's a list of A, and so the kata considers the list to be like the recursive thing, and the argument we're using is A, but then it doesn't care that the B is list of B. So it just so happens that the result is also a recursive structure, but the catamorphism itself doesn't care that the result is a recursive structure. As far as it's concerned, it's just some B that could be like a unitary value. And it's the same thing with Anna. So in the case of Anna, if you were constructing a list of like 10 elements that were all constant, you could say like, you could start with your seed value of like an int of 10, and then you do Anna and like just build up, I don't know, like 1, 2, 3, 4, 5, 6, 7, 8, 10. And that's like a straightforward, you're starting from like a single value and building up a recursive structure. But in this case, our A is like a little bit more complicated, so it kind of it is like a recursive structure, but you want to think as your tuple as just a single thing, and you're like slowly deconstructing it. Does that help?
It's better now.
Okay. Okay, cool. And so why do we want to do this? So the paper puts it pretty well. Separation, or in my paraphrasing, is separate the ingredients from the traversals. We crack this problem by treating various recursion schemes as separate higher order functions, giving each a notation of its own, independent of the ingredients with which it constitutes a recursively defined function. So what this is saying is basically recursion schemes is the filter or the map or the reduce that you're used to finding on the standard library list. So one thing, me personally, if I look at a Java code base, one of the things that strikes me, or even worse, like C++, like there's so many times you'll encounter this like for I equals 0, I smaller than I thing dot length, I plus plus. And you know, it's crazy. People are like rewriting this like day in, day out all the time, and it's a map. Or a lot of times, almost every single time you see this pattern in like a Java or C# code base, it's like a dot filter or a dot map or a dot reduce in Scala. That was like one of the first striking things when I switched over to Scala. And so this concept of higher order functions, let's encapsulate what we're doing and just leave out the very specific ingredients of this specific traversal that defines a very specific function. And that's very powerful because then when you're reading a code base, you can quickly see what's really special about this loop and quickly recognize the different traversals. And so recursion schemes is kind of applying this same idea at a higher level. So it's saying, recursions are great, recursion is great, it allows to express things in a very elegant way, but we're kind of doing the equivalent of like rewriting the loop every time when we're using explicit recursion. And really, when you think about the problem, there's really a handful of different traversals. There's a saying, I think, in the Matryoshka Gitter channel, it's almost always a kata. So really, kata is like the equivalent of map on your list. Like it's just something that you do like day in, day out, and there's no point kind of constantly redoing the explicit recursion. And I think doing this yields improved correctness because, I mean, it's kind of harder to write, but it ends up being more correct most of the time. There's another nice thing that you can achieve, which is fusion. So if you're doing multiple catamorphisms, you can end up kind of fusing them together, same way as if you're doing multiple maps, so that you only really traverse your data structure once and apply all the different ingredients that you kind of chain together. So sometimes it's easier to express things as a series of maps, but then for performance reasons, you want to just map over the data structure a single time. And another really nice thing is that when you're writing very purely functional code, oftentimes the functions that you want to pass into your higher order recursion schemes are monadic, right? There's error cases and stuff like that. And so in a library like Matryoshka, you'll notice that all the traversals have versions that finish with M that will do the binding for you. You know, if any one of the functions returns some error condition, then the whole thing returns an error condition. If all of the things works fine, then you get your result in the monad that, you know, tells you if things went wrong or things were fine. And you get that if you were to do explicit recursion, you'd be essentially like flat mapping all the time in your code, and that's really where you see the big savings in terms of code conciseness. So the general idea is I find that in general, when we can find ways to constrain the ways that we write our programs in ways that don't really truly constrain us, that we get a lot of benefits from that. And that's kind of what using recursion schemes ends up being, I think, is in a lot of cases, it does make writing the code harder, or at least you need to think about it more. But then once you've expressed it using these well-known constructs, it's much easier for people to later go on and look at the code and understand it and quickly identify common patterns. So that's what I wanted to share. I'm curious, what do you guys think? Are you going to try using recursion schemes in your next project? Questions?
What about stack set? Is Matryoshka and foundation stack set? Because in Scala you have doing all the things.
Yes. That's actually a good question. I'm almost sure that Matryoshka's implementation of traversals are stack safe. No, they're not? OK, Daniel says they're not.
If the monad you're operating in is stack safe, then like if you're using like an vector, but you can see this in Quasar. If you give us a big enough tree, the Q-script compatible with stack overflow.
So that answers the question. Yes?
I'd like to pick up on your last comment that it's harder to write those kata's in the first place, but then easier to see or to read afterwards. Why is it harder compared to writing straight up maps and flat maps?
So that's a good question. So why am I saying it's harder? Interestingly enough, if it's a really straightforward thing that you're trying to do, like a very classic kata, I would say it's easier, especially once you understand kind of the details of it. Usually, I mean, it's like the most succinct expression of it. It ends up being harder in some cases when you're not sure which one of the recursion schemes to apply, and in some cases, if what you're trying to do is very far away from any particular like pattern, if it's very like kind of custom. Yeah, there's definitely algorithms where I've sat down and it's like, oh, this is how I would write it if I could just use recursion explicitly, and it would be pretty simple. Same way as maybe a programmer 30 years ago is, I just want to put a goto statement here, and it's going to work, and I know it's going to work. And they kind of have to like, okay, but like how? And I remember when I was doing imperative programming, there were actually a few situations where I was faced with a loop, and I was like, if I could just like put a goto or like this break or continue or whatever, and like it ends up, you know, once I restructure it with loops, like it's easier to understand, but like it takes a little bit of work. So that's kind of what I was looking for, what I meant to say. So it looks like time is up. I can answer your question after, or one more question.
Okay. So in general, recursion schemes apply to other data structures other than lists.
Yes.
Right? So
yes.
All the recursive data structures. How do you characterize what kinds of data structures can be used in recursion schemes?
I would say any data structure that is recursive in nature. Say what? Right, yeah, except, oh right, okay, so yeah, a tree, like a acyclic recursive data structure, right. Awesome, thank you very much.